Hey everybody, welcome to the Systems of Human Performance podcast. This is episode 4, and today what I'll be doing is breaking down a couple of my recent articles on the Substack, namely one that focuses on the design of system response, how systems respond, or how we can design systems to respond to errors or anomalies that we encounter in different processes or the outputs of systems. And then I'm going to focus the second half of the podcast on looking at a different article, which is titled A Roadmap to Excellence, The Goodness of Systems. So we'll jump into that in due time. If you are listening to this for the first time and you have not already, please like, subscribe, leave a comment, do whatever you can to help me in the algorithm. That would be super helpful for me. I'll remind you again at the end of the show as well. So with that out of the way, let's go ahead and get started. I'll jump right into this one, the design of systems response. So essentially what is in scope in this article is something occurs. There is an error that occurs in a system. We are not meeting specifications some way. How does the system respond? How does the system identify that there's a deviation? And then what actions can we put in place to respond to this sort of thing? So I start the article by looking at like an industrial mixing process. I may have said it in a past podcast, but if I haven't, I worked one time as an intern at Domino's Pizza. And I wasn't in necessarily a franchise, but I was going around to all of the commissaries, is what we called them. And what they do there is they mix, at the industrial level, they mix lots of flour and dough to make the pizza dough. And what it kind of looks like is, you add you add flour and water and some kind of additives into kind of a dough, and then you weigh it. And then if you are wanting in weight, it's going to reapply it, and then finally, once it's at weight, it sends it over to the mixing process where it actually mix it, right? So you have to get the recipe right, and sometimes the machines that are working, they'll add too much flour, and then you have to add water because you've already added too much flour. So it's kind of this like recursive dance between the machines that are adding flour and adding water and the weighing scale. So that's just one way, just kind of as a vignette of how this process works. And then later on, as after the dough is mixed and it's put into balls, it goes through a metal detector to make sure no little pieces of metal shavings have fallen off. And again, there, when something happens and, hey, it's a deviation from standard, a small metal shaving comes off, well, it had this very big siren that would go off, and it would alert the workers to start throwing dough, just start pitching dough, because they don't want any metal shavings to get into the dough and into the customers. So hopefully you can appreciate right there, those are two very different system responses to a deviation from standard. In the one case, you have this kind of measurement and then this recursive action of the machine and the system automatically adjusting to it, adding flour, adding water. And then in this other one, you have kind of this pass-fail mechanism where it's just saying, is it good, is it bad? And then it alerts the workers to begin doing some sort of activity. So right there, that's just kind of what we're talking about, right? Is that how we design systems is very flexible, it's very versatile. It ultimately depends on what the task is at hand that we really care about doing. So we have a couple methods to jump into it. The first one is one that you might expect. I actually think I did another podcast on a different article that was all about kind of individual performance and what's actually capable for the individual without, really relying on systems. And this is what we see in self-monitoring. In self-monitoring, essentially, I am responsible for myself. I am responsible to make my own measurements, to make sure that all of my work product is within specification, so on and so forth. So, as an example, I have here in the article, a nurse might need to draw blood from the patient, and she, as the self-monitoring, will need to evaluate the condition of the syringe, the location of the vein, sterilization of the skin, insert the needle, begin the blood draw, stop the blood draw, and bandage the wound. Usually, if you've ever had your blood drawn, there are not two nurses working on you. There is not a whole mechanism there to support the nurse. They just trust the nurse's training to do the right thing, right? There's no greater mechanism in the system other than the individual, and that is something we call self-monitoring. Now, that's good. Again, like I said, all of these things need to be evaluated in the context of what we're hoping to accomplish. But, if you've ever had a nurse do this, she might often, or he might often miss a vein, not be able to locate it, struggle to locate it. There's oftentimes you run into lots of defects, actually, with regard to this very small and simple procedure. So I also list in the article just lots of different limitations of self-monitoring. It's very difficult, right, to maintain constant vigilance, to remember all the standards and criteria. The nursing one is actually very simple. She's not doing that every 5 minutes. It's not like a small cycle time. She may be doing it all day, but it's not like a production assembly line where you have to look at every single widget, 5 a minute or something like that, where you would need a much higher level of vigilance. Again, the standards and criteria, pretty straightforward, pretty easy from a visual inspection standpoint in terms of how she can self-monitor. She's not doing any sort of measurement or evaluation per se. So the standards and criteria are relatively easy. She can easily notice when something goes wrong, such as she's not getting a vein or the syringe is damaged. Again, it's very easy for her to identify defects and correctly diagnose the problem. All of these defects have a particular way they manifest, and it's very easy and apparent for the nurse. And of course, because of their training, they know how to implement the fix and identify what that fix is. So we can see there, relatively simple process is good. It is well situated for a self-evaluation process. Now, something else that we can do is we can start relying on other people to monitor our processes and our work products. So again, this is good because now it's independent. Now there are periodic checks. Now we have managers reviewing reports. Now we have editors reviewing written content, right? We have this kind of relationship between the work product and some sort of evaluator. Now, that's not just to say that that's the only way we can evaluate things is kind of with this independent monitoring. There are many other ways we can do it. One of the ways that I like the best is kind of this thing like concurrent monitoring. So I'll give you the example in the airline pilots, right? In aviation, you typically have a pilot and a co-pilot, and they're there to check one another at the same time to make sure that they both agree that all of the systems, all of the controls are in good working order before they take off the plane. Another great example of concurrent monitoring or kind of concurrent evaluation or inspection is that good old nuclear missile, right? Is whenever you have to turn the key to launch it, don't you need like 2 or 3 different keys in the suitcase in the football to make sure that we are all in agreement that this is something that we want to do, right? So that's a great example of how we're using concurrent monitoring. And then last, in terms of this monitoring by others, way we can configure our system is we have downstream inspection. And we typically see this a lot in manufacturing, right? Is we're going to manufacture a widget, it's going to go off the production line, it's going to go into some quality assurance process, and that quality assurance process is going to probably sample. They're probably not going to measure every single unit that's coming off the line, but they're going to measure them, they're going to sample them to make sure that these things are being produced in terms of the specifications that the customer needs. And if not, they're downstream, so they need to stop the production flow, go back upstream, figure out what's wrong, diagnose it, and then put it in order. So again, we see there it's a very different dynamic in terms of evaluation when we're talking about working with others versus self-monitoring. And indeed, the processes that we use in the monitoring of others are a little bit more critical. They're a little bit more complex than just what we might see in individual monitoring. So, for instance, manufacturing, where you're looking at many different measurements and their relation to tolerances. When you're looking at criticality regarding nuclear missiles and airline pilots, these sorts of things make a lot of sense to us. Now, what I like for this next method is essentially we can create an environment. Remember, our systems are every little input that affects our output, and that certainly means the environment. So we can create an environment that responds to errors or requires further validation before we move on to the next step. So one of the best ways to do this is by something called blocking, which is essentially we're going to block further progress through the process until we have validated that we're either the correct person with the correct credentials or authority or permissions, or that we're behaving in a safe way. So keys and locks, typically when you have a key, it means that you are given privileges to enter whatever is behind that lock, whether it's a safe, whether it's a door, so on and so forth. Our passcodes online, sign-on screens, right, they're all the same thing, is they're preventing us from proceeding in the process that we might like to do until we validate that we are the right person to do that and that we have the credentials in place to do that. We also can do things in terms of safety, right? So I think of the lawnmower that has that bar. It will not start until that, what they call the dead man's bar, is lifted up, and then you can actually start the engine. And if you want to shut off the lawnmower, all you have to do is let go of that bar and it will disengage the engine. The reason we're doing that is because it's a blocking strategy that we're saying you need to stand behind the lawnmower. You need to keep your hands away from the blade, and the best way to do that is to have this dead man's bar. Oftentimes in manufacturing with lots of cutting, you might see two-handed buttons where both hands have to be over a light sensor before the machine will actually be in place to prove that you're out of harm's way for the machine to do what it needs to do. So blocking, a great example of how we can design the system through our environment, particularly telling the environment that yes, we're the right person, or yes, we're behaving in a safe manner, and then the system can proceed in its normal process. We can also take this a little bit further and talk about forcing functions. So forcing functions are essentially things that prevent the behavior from continuing until the problem has been corrected. My favorite example of this is ground fault circuit interrupters, the GFCIs. So not only does the GFCI block unsafe activity, let's say I've got a short or there's water on the outlet, it's going to shut the circuit off. So that's blocked me from going further in the process. But it also helps prevent future failure because it's not going to it's going to alert me. One, it's going to give me a light that says, hey, this thing has been GFCI'd, GFCI'd, and you need to reset it and you need to make sure everything is safe, otherwise it's going to trigger again. And it will not clear, the ground fault will not clear until you have actually addressed what it was that originally set off the GFCI to begin with. So I like this quite a bit because it works. It's very consistent. The system is doing it. It's like an automatic response. So the system is not getting tired. It's not getting distracted. It's going to do the same thing every time. It's also immediate. So you run into this issue with things like downstream inspection because there's a latency, there's a lag between the action, you did something wrong, and then I found it out later on, right? So now there's a lag of feedback, and that instantaneous response for error queuing is so much better because oh, I did something just a moment ago that the system did not like, and now I can evaluate what that is and remedy it much quicker. And then, of course, there's clear feedback, right? There's no ambiguity. about whether something did or did not go wrong. The last thing is we can also look at all different types of automatic system responses. The error queuing is kind of like that, where it's an automatic system response, but it's something kind of like a dumb system response. So we can get more sophisticated, particularly in the age of technology and computers, with how the system can respond to errors. So we have things like gagging, where essentially the forcing function prevents users from doing something further, right? So something went wrong, and now the computer is going to lock the keyboard to prevent further typing. We're going to stop where we are, and we will not prevent further use. The GFCI is a little bit like that too. We can also give warnings. If you've ever dabbled in Excel, sometimes you'll get a you'll get like an error code that says, "Hey, this formula is not working. It's a num error or it's a value error." It tries to tell you that you are in a potentially bad situation, or maybe a dangerous situation, or a situation where the calculator is not rendering the number that you might have expected it to. And it also tries to inform you of what that might be, but it ultimately lets the user decide what the ultimate decision should be. Should I go and address that error, or should I just skip it? Because I know, yeah, I'm dividing by 0, but whatever. I know that that's pretty much just 0, or something like that. We could also do nothing, quite a valid option, right? The system might just say there's an error, but I'm going to ignore it, right? Sometimes this is a very valid response, particularly for non-critical variations. So if there's a small deviation or something like that, system doesn't have to respond to it. We can also do a self-correction, where the system identifies the error, determined what the desired goal was, and then makes adjustments to reach the desired goal. This is very sophisticated. You might be familiar with spelling corrections on your smartphone, also in Microsoft Word. This in itself may have possibilities for errors, right? So the self-correction itself might also have errors. It does this all the time when I pull out my phone and it says, no, you really meant to say this, and it self-corrects. Sometimes that creates an error too. But in the age of artificial intelligence and this kind of new emergent technology, this is going to be what many different technological systems are going to be moving towards, which is moving the operator out of it, or just for kind of critical or really difficult errors or deviations. But for routine errors and deviations, we're going to more and more be relying on self-correction. We can also do a couple more things. We could talk about it, where this is also more prevalent in the age of AI, where the user and the system engage in a sort of dialogue to detect and fix errors. When you think about coding compilers, this is exactly what they're doing, where, syntax error. Oh, can you tell me which line the syntax error was on? Okay, it was on line 42. Well, now I can go onto line 42, figure out what that syntax error is, and make the remedies and the adjustments as needed. So we kind of get into a dialogue with the system, where the system is providing us more specific feedback, not just a pass-fail on whether or not there was or was not an error, but instead on specifically what the error was, what the type of error was it a syntax error, was it an object error, and where that error is occurring. And then lastly, we can start to teach systems to detect issues and requests. This is ultimately how things like machine learning become what they are, right? Is we're going to teach a machine how to categorize these things. We're going to give it a training set to train, and then it's going to predict future values. So in this way, we're essentially loading in a bunch of perhaps errors, and then we're telling the machine, okay, if you get an error that looks like this, I want you to do procedure A. And if you get an error that looks like this, I want you to do procedure B. With artificial intelligence, not just LLMs, but we see this a lot with like image processing, right? It's, hey, I'm going to train you on what these images look like. I know somebody who's a coin collector. they built this machine that was, used AI imaging to look at whether there was a rare coin in his stack of quarters or something like that. So then this machine would run through, image every single coin, and then if it met criteria for this rare coin, it would move it to the left. Otherwise, it would move it to the right, right? So we can teach systems to respond based on certain criteria. So that is pretty much what I wanted to talk about in this podcast episode of this article. The article goes on to discuss lots of other things, the hierarchy of effectiveness, practical applications, how to choose the right response method. As I said, it really depends ultimately on what the system needs and how the system is configured to begin with. But just to be aware that yes, we do have flexibility, we do have agency to design how systems respond in the face of errors. We have flexibility to define what those errors are, if it's just a pass-fail, if it's a measurement deviation, or if it's something categorical, like sorting coins. Okay, so that takes us through the end of this first article, Design of System Response. And now we'll flip over to this other article that I wrote called A Roadmap to Excellence, The Goodness of Systems. And what I've done here is I've just kind of taken all of my observations, kind of the things I've read and the things I've seen, and I've broken them out into this natural progression of interventions. So I use this example of I used to go to the University of Michigan. It was kind of like the engineering school was on North Campus, so lots of people commuted, they took their cars, and the parking lot was always filled with different vehicles. So, and of course they were unauthorized. They were students who were in the parking lot, and they were supposed to, be faculty and staff and things like that. So the first thing that they typically do is they typically tell you that you've done something wrong, right? Please don't park in the faculty lots. There are student lots available here, here, and here. And they show you that the student lots are a half mile away, and that's where you're supposed to park. This is also true in manufacturing. It's true in industry, right? Is they're going to try to tell you what the proper thing to do is, right? They might train you to a standard. They might give you 1-point lessons. Wear your PPE, wear your safety glasses, wear steel-toed shoes. And that's usually the first step. When that fails, when you still are observing errors, anomalies, issues, whether that's wearing protective gear or the students parking in a parking lot, they then start to give you signs and visual reminders. Hey, if it's the parking lot, this is the faculty parking lot only. Student parking is in lot B. Or, you'll have, signs that say, wear safety glasses before entering the production zone or something like that. And again, they're better. They're visual reminders. And then they move forward. They're still seeing lots of errors, issues, variations. So then they start to do things like permits and identification. So in this case, the faculty lots, right, is they're going to give you authorization, kind of trying to use that forcing function, the environmental cueing that we saw from the last article. Ultimately, what they're going to rely on then is enforcement, right? In manufacturing, you have this very strict lockout, tagout enforcement, where if you don't lock out the machine, you're going to be fired because it's a critical safety violation, and there is no tolerance for that sort of thing, and so forth. So therefore, you're going to be fired because you're doing this thing, and now there's a monitoring in place, and there's an oversight in place, and there's an enforcement in place. I also saw this at the university in the parking lot where they would actually have a patrol car standing or parked outside of that lot to make sure that students weren't going to the parking lot. But eventually what you really need to do is have physical prevention, is eventually have something in the environment, a forcing function or something like that, that ultimately prevents those students from parking in the parking lot, right? And what we actually saw at the university is they put in a toll gate where, of course, you scan your badge and the toll gate opens, and now you go in if and only if you are authorized to be in that parking lot. So here, this is what I call the natural progression of interventions, because this is typically how people respond. It takes the path of least resistance. If I can just train you or communicate, that's great, and I don't have to put in that much work. But then I'm starting to do more things, right? I'm starting to use visuals. I'm starting to use signage and notifications. And then I'm starting to even get into like a really, really, kind of expensive intervention, right? Where now I have this ongoing enforcement and oversight versus physical prevention. And what we actually see is this is not only a natural progression of how people engage in trying to reduce errors or trying to get get the system back to standard, but there's actually also this natural progression of what I call the goodness of systems. So if systems are designed in such a way where they rely on those physical properties like the toll gate, like the gagging, like the keys or the forcing functions that we just talked about, they're excellent systems because they prevent errors from occurring to begin with, right? If the system relies on things like downstream inspection and warnings and that sort of stuff, sirens, lights flashing, well, they're good because they're notifying the operators or the people who are using the system that there's a deviation. But and typically, not so much the case of the students who are grossly violating the laws and the standards. But most cases, when we engage in systems, particularly in industry, we're trying to do the right thing. We're trying to do the purpose of the systems. We just might be deviating from the way the system was designed. And we need to get back that way. So obviously air proofing, preventing that deviation from occurring in the first place is best. Otherwise, we want to warn them or do some sort of downstream inspection. And that's good. It's not as good as preventing the error from occurring to begin with, but it's good that we can inspect and enforce and also warn people of doing something. And then way down at the bottom is kind of that focus on the individual or on individuals, right? The relationships between one or more people. And we have things like 1-point lessons and written standards and visual standards, right? So the whole idea here is that if I can build a system that takes it out of the hands of the individual, takes the possibility of defects out of the individual, and puts it more into the system. And it can do that ideally through those forcing functions and air proofing, but it could also do it in terms of alerts and sirens and noises and air horns and that sort of stuff. But in as much as I remove myself as the individual from making errors, and I put that responsibility or that response or that notification onto the system, my system is that much better for it. My propensity to cause errors or anomalies or issues has been reduced, and now I'm more productive and more efficient as a result of it. So that is really the whole idea of the goodness of system spectrum. So I'm just trying to remember if there was anything else that I really wanted to talk about in this article. You can see there's lots of different lists. There's lots of different, I get into detail about different things in terms of air proofing and inspection. I will say one of the big things that people often fail in understanding is inspection and enforcement are extremely, extremely good at bringing the system back into standard, but they're also extremely expensive. And it's this ongoing cost of enforcement and inspection. And I give the situation of seatbelt laws, right? Is we know that there are officers who will watch to see if you're buckled up, right? And if you're not buckled up, they will enforce that and they'll give you a ticket, right? So there's the inspection with the police officer looking to see if you have your seatbelt, and then the enforcement, right? Is if you don't have your seatbelt buckled, they're going to issue you a ticket. So that works. Most people have their seatbelts in place, but we could actually eliminate all those police officers from needing to do that, from needing to just kind of do this banal inspection of whether or not people are buckled up, if we used one of those tools from our design of system response. If we used something like an interlock, where, you know what, the car's not going to start until you've buckled up, well, now I don't have any officers going around looking to see if I am complying with the seatbelt law, because I know my vehicle won't start without the seatbelt being buckled up. Now, that doesn't prevent, people from unbuckling their seatbelt while they're driving, but it certainly is going to reduce those instances. Many people, once they're buckled, are not going to unbuckle themselves just because they don't like the seatbelt in place. So all that to say, in terms of system design, and particularly looking at the design of system response, it's really, really important to understand that we have flexibility on what we can put in place and how we choose to respond to errors. In terms of the goodness of systems, we should always be striving for that error-proofing setting. We should always be trying to prevent errors from occurring in the first place, whether those are like fail-safes like the dead man's bar, or for the lawnmower, or there's something else like the toll gate, right? That's preventing unauthorized people from getting into a parking lot. And the design of system response is an integral part of that, because it's telling us all the different options we have in achieving that error-proofing level of goodness. So that's really all I wanted to talk about on today's podcast. Two really good articles, two articles I'm really passionate about and I get excited about because they make a big difference. And also the error-proofing stuff, the stuff we've talked about, they don't cost a whole lot, do they? Keys, interlocks, there are a couple lines of code, there are a couple pieces of steel. They really punch above their weight in terms of what they can deliver to a system in terms of reliability, resiliency, productivity. So I hope you've liked this podcast. I hope you like these two articles. Please go check them out. It's free to everyone. There's no paywall behind it. If you like this podcast, if you like what we're doing at Systems of Human Performance, please like, subscribe, interact, do whatever you can to help us out in the algorithm, and I really appreciate it. Thanks.